So 15.2 is solving equilibrium problems. The key in success in solving equilibrium problems is to make sure you understand what assumptions can be made, or if assumptions can be made. If you are able to determine that these assumptions are valid, then the problem will be so much easier. And for those of you in lab, you are going to see that in experiment number 2. You guys are going to determine the equilibrium constant of an iron thiocyanide formation, and you're going to make certain assumptions to get the equilibrium constant for that particular experiment. So let me go ahead and get started here. And for those of you who are having difficulty in math, the math level in this section is algebra and the quadratic equation. Okay, if you don't know how to solve the quadratic equation, use a quadratic formula calculator, but it's basically just making sure that you plug it into the formula to solve quadratic equations. So let me go ahead and get started here. Okay, solving equilibrium problems. They're basically just two types with variation. One is you're given the concentrations of the chemical at equilibrium. It's at equilibrium, and then you're asked to calculate the equilibrium constant. That's pretty straightforward, with some tweaks. As long as you know the mass action expression, again, I remind you that it's the products over a reactant raised to its coefficient, excluding solids and liquids. Okay, excluding solids and liquids. So you stick it into that mass action expression, and then you solve for K equilibrium. So the conditions has to be that the concentrations in that mass action expressions are at equilibrium. That's the key. The second part is what you guys learn in general chemistry, except with a twist. In general chemistry, you're given the starting ingredients, the reactants, and you're asked how much product is formed based on this reaction. The difference between general chemistry and Chem 201 is that it doesn't go to 100% completion. There is a point where you get products, but the product is determined by the equilibrium constant. The equilibrium constant is an indicator of efficiency. It'll tell you whether it's 90% complete or 10% complete. That's what equilibrium constants provide. Okay, so keep that in mind. So these are, like I said, the two types. The first type is given the concentrations, solve for the equilibrium constant. The second type is you have the equilibrium constant, you have the initial conditions, solve for the concentrations at equilibrium. Solve for the concentrations when it seems that the reaction has stopped. Okay, that's the second type. And we're going to explore both types in today's discussion. So type 1 seems pretty easy, but it can be twisted around, so you guys are scratching your head. But let's take a look at a few of these problems first. Okay, the first thing that you should always do, especially in a chemistry problem, is if you have a chemistry problem and it involves a chemical reaction, make sure that the formula for all the chemical species are correct. If it tells you sulfur trioxide and you write SO2, you already are going to have the wrong solution. Why? Because you're starting out with the wrong premise. Make sure that the formula for all the chemical species are correct, and then make sure it's balanced. Inspect the phases, because when it's a liquid and a solid, they don't go into the mass action expression. But the balanced equation is key, because remember, in the mass action expression, you're raising all the concentrations of either your aqueous or your gas phase chemical to the coefficient. So if it's not balanced, all bets are off. You're going to get the wrong solution again. Okay, so that's critical. You gotta follow up on the fundamentals. If you don't follow up on the fundamentals, making sure that the formula is correct, balancing the equations, making sure that you have the correct phase, then you're already going down the wrong path. Okay, so in this particular problem, you are generally given the concentrations at equilibrium. You plug it in, you write the mass action expression. Okay, write the balance equation for the reaction. Make sure that you have the formula. Write the equilibrium expression or the mass action expression. That's products over reactant raised to the coefficient. And plug the equilibrium concentrations in the mass action expression and solve for K equilibrium. Now, if the information that you have for the reaction is concentration, then you're solving for K sub C, equilibrium constant in terms of molarity. Excuse me. If the chemicals that you are dealing with is expressed in partial pressure, then the equilibrium constants that you're solving for is K sub P. And remember, both of those are related by the ideal gas law. K sub P equals K sub C times RT raised to the delta N power. We talked about that last time, where delta N is equal to the moles of the gas on the products, that's the coefficient, minus the moles of the gas in the reactant, that's the coefficient, that's delta N. So let's take a look at this problem, and I'll try and break this problem down so that you guys start thinking and about how to set up a problem rather than just diving in. Okay, take a look at this problem. First of all, carbon dioxide is placed in a 5-liter container. So that's the volume. Okay, that's the volume. If it's 1 liter, great. Whatever moles you have in that 1 liter is the molarity. Why is molarity important? Because when we have equilibrium problems and we're dealing with K sub C, it has to be molarity as the variable that you put in the mass action expression. Molarity, so you need moles per liter. But anyway, we have a 5-liter high pressure reaction vessel. It's at 1400 C. You may or may not need that particular temperature. We always quote the temperature because the equilibrium constant is a function of temperature. As soon as we change temperature, that equilibrium constant will change. Okay, so we quote the temperature here. We say that this is the volume, this is the temperature, and then we're given the following conditions. Yeah, we start with CO2, but CO2 will decompose to CO and 1/2 oxygen, as shown in the balance equation. And then it doesn't really matter whether CO2 decomposes to CO and oxygen, or CO and oxygen combines to CO2. What you need to do is look at the equation in question and see whether or not the equilibrium constant applies to the equation in question, or whether that equation should be reversed, in which case the equilibrium constant that's provided is the reciprocal value. Remember, we talked about that last time. Anyway, this is the reaction. Carbon monoxide plus 1/2 an oxygen goes to CO2. Okay, note the coefficients in that balance equation. Note that all species are gas, and even though they're gas, you can still quote the amount by molarity. Why? Because we know the moles and we know the volume. Yeah, it's a gas in a container, but as long as there's a mole in that container in a specified volume, you can calculate the molarity. And of course, you can also calculate the partial pressure based on PV equals nRT. That's what temperature is given. Okay. But again, we're trying to make sure that you understand the chemical process that's occurring, because when you can visualize it, then perhaps it'll be easier for you to express it in a mathematical equation. Okay, this is the equation, and then you want to know you're solving for Kc and Kp. That's what you are solving for. But you also want to know that these are the moles of the chemicals at equilibrium. Equilibrium is achieved, and these are the moles that is found. That's probably the most difficult part in reading word problems, is to figure out whether the information that's provided is the initial amount or the equilibrium amount. So you have to hone into keywords in trying to figure that out, okay? But this is the equilibrium amount. So let me draw you a picture. You have a reaction vessel. It's a high pressure vessel. The volume is fixed, and that's 5 liters. The temperature is fixed. They don't tell you you change the temperature. That's 1400 degrees Celsius. If we're going to use it, of course, in PV equals nRT, you need to add 273 to that, because whenever we have gas loss, you're always taking the absolute temperature. And then we have CO, O2, and CO2 in here. And the chemistry is occurring where those are the only chemical species that is involved. So this is the reaction that is provided right here, okay? This is the reaction that's provided. And this is the equilibrium. You're trying to calculate the equilibrium constant for that reaction. You're not trying to calculate the equilibrium constant for the reverse. So what you need to do is, of course, write the reaction. Carbon monoxide plus half an oxygen goes to CO2. This is what I like to call an ice table. Some texts will introduce this as an I delta E table. The ice means initial, change, that's why we can use delta as well, and equilibrium. Let me try and explain why we use this systematic way of solving equilibrium problems. That's because when we have a reaction, you can think about a reaction in terms of what are the conditions before the reaction starts. Usually before the reaction starts, you only have reactant. Sometimes, however, before the reaction starts, you can charge this container with products and reactant. And in this particular problem, what we have is carbon dioxide. So if we charge it with carbon dioxide, how can we write that reaction? Well, we bring it back to the reverse reaction, and then we think about that reverse reaction occurring when there was only oxygen and carbon monoxide and then CO2. That's really not as important because the problem presents the equilibrium condition. But again, I want to stress that this is the initial, sorry, the format. This is the initial concentration, and then this is the initial condition. Okay, the initial condition right here. You have a certain amount of CO, a certain amount of O2, and usually when the reaction starts, no product. But that's not this problem. Okay, that's not this problem. Why? Because they give you the equilibrium condition. Now, when the reaction progresses, you look at the stoichiometry, and the stoichiometry tells you for every 1 CO that is consumed, you need half an oxygen to produce 1 CO2. So that's the delta. That's the delta. And you see this more in terms of how it's applied when we go to the second part of solving equilibrium problems. But for now, there's an initial condition. There's the change that takes place as the reaction goes to completion, or the reaction goes to equilibrium, okay? And then you have the equilibrium condition. That's when everything's steady. So that's exactly what we have right here. It tells you when equilibrium is achieved, you have 4.95 moles of CO2, 0.0500 moles of CO, and 0.0250 moles of oxygen. So I'm just writing this right below the chemicals. Again, you have to be an accountant when you solve these things so you can keep track of what the chemicals are doing in the progression of the reaction. Okay, now those are moles. That's not molarity. You need to divide by the volume. And then you have the concentrations. Once you have the concentrations, the molar concentrations, then you can plug it into the mass action expression. It's pretty straightforward, isn't it? Okay. Problems like this, you guys should be able to get 100%. You just have to make sure that you follow along with the math. And so let me move to this part right here. This is exactly how you would solve this problem. You'd put the moles there, and then dividing by 5, these are the equilibrium concentrations. 9.90 times 10 to the minus 1 molar, 5.00 times 10 to the minus 3 molar, 1.00 times 10 to the minus 2. Now, notice I'm using 3 significant figures in the equilibrium, whereas I'm given 2 significant figures here and 3 significant figures here. Carry as many significant figures in the intermediate problem, in the intermediate calculation, so you don't have rounding off errors. That's always good practice. And then in the end, round off. Okay, that's my recommendation in terms of solving math in chemistry. Carry as many significant figures in the intermediate calculations, round off at the end. That way you don't have rounding off error. Now what we want to do is write the mass action expression. The mass action expression is, this is Kc, okay, and that's equal to CO2, and the bracket again means molarity, oxygen to the 1/2. Why 1/2? Because we have 1/2 there. Remember that when you raise something to 1/2 power, you're taking the square root of that number, and then CO. Looks like that, and that would be Kc. We would need to calculate Kp as a secondary, as another solution to this question, because that's what it's asking. But let's take a look at Kc for now. We just plug it in. Let me erase that so you guys can see. Okay, this is basically it. 9.9 right here. 1.0, that would be the carbon monoxide, and then 5 times 10 minus 3 to the 1/2, that'll be oxygen, and you get 1.40 times 10 to the 3rd. I would probably round this off to 2 significant figures, just because, no, they all have 3 significant figures. They all have 3 significant figures right here, 3, 3, and 3 significant figures. So you would keep 3 significant figures, okay? So what would Kp be? Kp, remember this equation, equals Kc RT. Remember, this is positive, P for positive. So this is positive delta N, positive delta N. Okay. So what is delta N? Look at the coefficients in this equation. Look at the coefficients. This is 1. When there's no number in front, it's assumed it's 1. Okay. If it was 0, it wouldn't be there. Okay. So when there's no number in front of a chemical in a reaction, you assume it's 1. It is 1. This is a 1/2, and this is 1. So 1 products minus reactant minus 1/2 plus 1. That's the reactant. This is product. And this comes from that, and this comes from that, and that. Okay, it's the coefficient in the balance equation. So that delta N equals minus 1/2, or, oops, minus 0.5. 1 minus 1.5 is minus 0.5. So Kc is equal to 8.314, Kp, and this of course will be 1.40 times 10 to the 3rd. 8.314 times, that's where we use this temperature, 1400 plus 273. Remember, we need absolute. That's 1673 times 1673 to the negative 0.5. Now you might say, but I thought this was positive. Yes, that's positive delta n, but delta n is negative 1/2. If delta n was 1/2, then it would just be positive to the 0.5, but delta n is minus 1/2, so we have to put a minus 1/2 there. Remember that the negative tells you it's a reciprocal, the 0.5 tells you it's a square root. So this problem really is this right here. Let me clear some space over here. So this problem looks like this. Oops. Kp equals 1.40 times 10 to the third all over 8.314 times 1673 square root of that. That's what negative tells you it's a reciprocal, 0.5 tells you it's square root. So I put these values in the bottom, and then I took the square root of that. If you take a look at the solution, that's exactly what I did right here. Let me clear this. Okay. It's exactly what I have right here. Okay. This is 1.4 times 10 to the third. Sorry. I got a brain lapse. R does not equal 8.314. Why? So for equilibrium problems, we didn't need whole, you don't need whole number formulas. It could be a half. R here is not 8.314. I keep forgetting my R's. Why is it not 8.314? Because we're using the ideal gas law, PV equals nRT. Whenever we have atmospheres, then the R value is not 8.314, it's 0.08206. Liters atmosphere, mole Kelvin. Okay, if we change liters atmospheres to joules, okay, then it's 8.314. I don't know why I was using 8.314. I'm still thinking about kinetics probably, but we're using 0.08206 for R. 1673 is the temperature. We raise it to the negative 0.5. That's like putting it in the reciprocal, the bottom. You're dividing by that and taking the square root, and you get 1.2 times 10 to the second. Okay, 1.2 if we follow the math. So believe it or not, I spent like 20 minutes on that problem. That's an easy problem. It gets more difficult, I'm sorry to say. But I want to make sure that I spell out the little things that you will forget. What are the little things? That you have to use the coefficient when you're calculating delta n, that you're using molarity here because it's simpler. You could easily have converted to partial pressure using this for all of these right here. If you just plug it in here, you could easily calculate K sub P because you know the volume, you know R, and you know T. So you can get the partial pressure for each one and then just calculate K sub P directly from that. Okay, there's other ways to get to K sub P. You don't have to use that equation, K sub P equals K sub C RT delta N. You don't have to use that equation. There's other ways of getting there. And you need to be able to recognize that. Okay, so let's move on. Here's a different problem. It's still determining K equilibrium. Okay, this one will require you to think a little bit deeper. Okay, we have a mixture of carbon dioxide, hydrogen, water, and that's basically the reaction. Carbon dioxide plus hydrogen goes to carbon monoxide and water. The reverse of this reaction is actually called the syngas reaction. And if you can take carbon monoxide, which is really bad in water, you can produce hydrogen. And if you read the news lately, especially in the electrical vehicle or the fuel cell vehicle, fuel cells requires hydrogen. So we can produce hydrogen by reversing that reaction. It's not as economically feasible yet compared to the price of gasoline. But if the price of gasoline becomes, or gasoline becomes rare, fossil fuel becomes rare, or we're more concerned about our environment, then this is a reaction that might pan out. But anyway, we're not looking at the reverse, we're looking at the forward. So let me erase that. Okay. So we have this reaction, carbon dioxide plus hydrogen goes to CO plus H2O. We're looking at the reverse. It tells you a mixture of 0.1 moles of CO2, 0.05 moles of hydrogen, 0.1 moles of water is placed in the, let's see, in the reaction, is placed in a vessel. Again, we have a vessel, that's just a container. The following equilibrium reaction is established. So we basically have this reaction, CO2 plus H2 in equilibrium with CO plus H2O. They're all in the gas form. They're all in the gas form. I'm going to generate my ice table. Why? Because the ice allows me to account for what's happening to the chemicals as the reaction progresses. Let me see. The following equilibrium is established at equilibrium. Now we're at equilibrium. Okay. CO2 equals 0.0954. And calculate the equilibrium concentration of hydrogen, CO, and water. Calculate Kc for the reaction, and calculate Kp for this reaction. So we know the equilibrium concentration for carbon dioxide. That's what's provided in the problem. Okay. We also know, yeah, real quick. We also know the initial concentration of carbon dioxide. That's 0.1 moles. And you see how we have 1 liter? That's great, because 0.100 moles is 0.100 molar. I can just do that. The hydrogen is 0.0500 molar, and then the water is 0.100 molar. Okay. There is no carbon monoxide in the initial condition. When we charge up this vessel, all we had in here was CO2, H2, and water. There was no CO. But the CO will form when the reaction begins, because CO2 and hydrogen will produce CO. Okay. So let's think about this reaction. So these are the initial amounts. All you have are these chemicals. Now what will happen is that these two will form water plus CO. So this is where the delta line comes in. This is the amount that we have, but delta tells you there is going to be some amount CO2 that's used. We're going to use the variable X. I could easily use Y, I can easily use Q or N. It's just a variable that you guys will need to solve. So for every carbon dioxide that is consumed, you also consume an equal amount of hydrogen. That's just based on the stoichiometry. For every 1 carbon dioxide, you need 1 hydrogen in equal amount. It's not half an oxygen, it's not 2 hydrogen, it's 1 oxygen, because the balance equation tells you that. And then you produce, that's where the positive comes in, the same amount of carbon monoxide. How much? X amount, X amount. That's what you need to solve. You don't know what that amount is. In any moment of time, that amount will vary. But at equilibrium, that amount will be fixed. Okay, at equilibrium, that amount will be fixed, and this will be X as well. Now, if you had a 2 here, then that would be 2X. Okay, we don't have a 2 there, we only have 1. So let me make sure that you are consistent. This is very important, because this is your accounting of what's going on. So if you look at this problem, you can see that, well, I don't know what this is. I don't know what this is. I don't know what this is, but I do know that And so I can write the mass action expression, K equilibrium, in this case, Kc is equal to H2O concentration, which we don't know, the CO concentration, which we don't know, the hydrogen concentration, which we don't know, and we only have carbon dioxide concentration, 0.0954 to the first. And so you might say, well, we have one equation, three unknown. So you're going to have to step back and think more deeply, okay? And think about, there's another piece of information there that will allow you to solve this problem. And that other information happens to be right here. If you have 0.1 molar CO2 and you remove some X, and then you end up with 0.0954, then you can solve for X. Then you will know exactly how much of that carbon dioxide is consumed when it reaches equilibrium. That's the key, because once you solve for X here, then you know what X happens to be for all of these. And if you know what X is, then you can solve these problems right here. 0.1 plus X, that's the concentration of water. 0, because we don't have carbon monoxide, plus X, that's the concentration of CO. 0.050 minus X, that's the concentration of hydrogen. So you have to look beyond the problem and not just kind of have a one-dimensional outlook. Otherwise, you're going to get stuck. So that's what we are going to see here. Okay, my other computer died. Here in this solution right here, let me clear this out for you so you guys can see how I work this out. Okay, so right here, I solve for X. 0.100 minus X equals 0.0954. So solving for X, that's 0.0046. That means this is 0.0046. X is the same for all of them. Now, if this was 2 here, then you would put 2X or 0.0046 times 2. But of course, it's not. But I just want to illustrate that to you. Okay, that's why the balance equation is so important, because it tells you how to account for the chemical species during a reaction. So once we have all of this, then we can easily stick it into the mass action expression. Okay, well, we can solve for that, solve for that, solve for that. Remember, products are always going to be plus X because they're being formed. Reactants are always going to be minus X because they are being consumed. So now we have the equilibrium condition. We can just stick it into the mass action expression. We have this right here. Okay, we're plugging and chugging. That's what we are doing. And it comes out to 0.11. The second part of this problem is calculate Kp. This is a super easy problem for Kp, because if you look at delta N equals 2 minus 2, that's 0. Anything to the 0 power is just 1. 1,346,000 to the 0th power is just 1. Okay, so please remember that. So K sub P is just 0.11. It's the same, because RT is taken to the 0th power, because that's delta N. So Kp equals Kc. Okay, that's what we see right here. Oops, that's what we see right there. So those problems are of the easy variety. In a scale of 1 to 10, 10 being the most difficult, these types of problem, the second problem is probably a 3, the first problem is probably a 1. Let's go into the 6 or higher type of problem, okay? So hopefully you guys understand the fundamentals here. The fundamentals is that you need a balance equation. You need to make sure that you pay attention to the phases and know how to write your mass action expression. Know the meaning of your ice table. So let's take a look at the second type of problem. Second type of problem is going to be this right here. Let's see what's going on here. Oops, wrong class. Sorry, my other computer shut down, so I'm trying to get on to Zoom here so that I can see what I'm presenting and I'm not totally lost in terms of what you guys are seeing. So let's take a look at this problem right here. In this particular problem, you have a secondary type of problem. And again, I want to make sure that I am deliberate in showing you how to think through these problems, because these problems are going to be one of your more difficult types of problems. And then these problems are the fundamentals for acid-base chemistry. Okay. So when you have this type of problem where you're given the initial conditions and you want to know how much the concentrations are at equilibrium, you're going to be given that information initial. You're probably given an equilibrium constant, or you've calculated an equilibrium constant so you know what that value is. You need to make sure that you balance the equation, pay attention to the phases, make sure you know how to write the mass action expression, list the initial condition in the ice table, show how the changes occurs with the change in the ice table, minus x or minus 2x, depending on the coefficient in the balance equation. Okay, and then solve for the x value, because the x value, when you plug it in, will tell you what the concentrations are at equilibrium. So this is the strategy to use in solving these types of problem. Okay, so, and then of course, assign x to whatever chemical you're trying to figure out the equilibrium concentration for and solve that. So let's take a look at this problem. This is sulfur trioxide. It's formed when SO2 and NO2 are mixed in a reaction vessel. And that's all I give you. You guys should have the knowledge now that if I have a reaction container and I put SO2 in here and NO2 in here, and I tell you that one of the products is SO3, you could probably figure out what the other product is, okay? Just by looking at the reaction. So the reaction will look something like this. SO2 plus NO2, and these again are going to be, let's say it's a gas. An equilibrium of SO3 plus, and if you look at this problem, one of the SO2 picks up an oxygen. Where does it pick up the oxygen? Probably picks it up from NO2, which means that NO remains. Okay, NO remains. Even though I didn't give that to you in the problem, you guys should, with enough chemistry, you guys should know where that oxygen come from. Came from NO3, sorry, NO2. That means you have NO remaining. And NO is a certainly very stable chemical. Okay, it's a stable chemical. It's actually a free radical. It's a chemical that has an unpaired electron, if you guys remember your general chemistry. So we have an initial, a change, and an equilibrium. It tells us how much is formed when 0.5 moles of SO2, NO2 are in 1 liter at 821. So it's asking us how much of this is formed when S.5 and are in a 1 liter container at 821 degrees. Okay, that is not the equilibrium conditions. That's your beginning conditions. That's your start. That's your start concentration. Okay, so how would you know that? Well, you have to have enough. I'm sorry that you have to have enough. Let me make sure that you guys can see this. Experience to know that. Got to have enough experience to know that. So working out these problems will help you gain the experience to know that your initial concentrations. Okay. I'm looking at something here. Hold on. Okay. Yeah. So let's go ahead and fill in this ice table. We have, again, we have 1 liter. Whenever you have 1 liter, that's great. You don't have to take the moles and divide it by the volume. The moles in 1 liter is the molarity. So the molarity of SO2 is 0.50 molar. Okay, because in the mass action expression, we need molar. This is 0.50 molar. This is 0 and this is 0 because the reaction hasn't started yet. You have to make that assumption. The reaction hasn't started. Then, according to the balance equation, this is minus x plus x plus x. So what exactly is the concentration at equilibrium? We can't give it a number, but we can give it a mathematical expression. This is 0.50 minus x. This is 0.50 minus x. This is x, and this is x. So the mass action expression, in this case, K sub C, because we're dealing with molarity, equals this. X times x, that's these guys right here, over 0.50 minus x, 0.50 minus x. This is x squared over 0.50 minus x squared. Now, the brute force method would be actually to multiply 0.50 minus x out. That's just, you multiply that out and then solve the quadratic. Okay, and then you're given an equilibrium constant here of 6.85. That's what you guys need to solve. What you should recognize, for those of you who are mathematically inclined, is that this is a perfect square. 6.85 equals x over 0.50 minus x squared. That's an easy problem to solve. You take the square root of both sides, and you get x over 0.50 minus x equals the square root of 6.85, and the square root of 6.85 happens to be 2.62. You can solve that problem for x. You can say x equals 2.62, 0.50 minus x, and then it's equal to, remember the law of distribution, that's 1.31 minus 2.62x equals x. Anyway, you solve that math. You guys should be able to do that. Okay, here's the solution right here. Let me show you that. Let me clear this up so that you guys can see. Okay. There's the solution. It's a perfect square. You take the square root of both sides and you get that. The constant, the x value, when you solve this, is 1.3. So that means that this is 1.3. This is 1.3, but this right here is 0.50 minus 1. Sorry, not the value for x is going to be, in this particular case, let me just double check this. No, here is the amount. Okay, so that's the value that we would get. Let me just double check this. Oops. X is not 1.3. X equals 1.3 divided by 3.617. X equals 0.36. Now, how did I recognize that I had a mistake there? I recognize that, and you guys should do this too. Be able to recognize that 1.3 is not the true solution, okay? Because 0.50 minus 1.3 is going to give you a negative concentration. No such thing as a negative concentration. So if you can catch your mistake in mid-calculation, then you can see where you made your mistake. And like me, I just looked at that number because I saw this, but I didn't really look deeper that 3.617x equals 1.3. And so when you do this, x is really 0.36, not 1.3. And I recognize that I made a mistake because when I put 1.3 right here, it gave me a negative value. No such thing as a negative concentration. It can be close to zero, but doesn't make sense physically. Doesn't make sense physically, okay? So again, this particular problem illustrates to you how you would use the ICE table and a little bit of math in order to solve it. And this is actually a pretty easy problem to solve. Why? Because it turns out to be a perfect square. Turns out to be a perfect square. So the math simplifies. The math simplifies. Recognize that in your problems. That way you don't go into, I remember when I was in general chemistry back in the days when I was taking this, some problems, and then I take a course like physical chemistry. Some problems takes an hour just to solve, maybe a couple hours, just like your calculus class probably, okay? And sometimes it takes that long because you make a mistake along the way, and then you realize that answer doesn't make sense, so you have to backtrack, okay? But if you start with the fundamentals and you recognize your mistakes, it shouldn't be that long. Let's move on to the next type of problem. Same problem here, except now I change something. I change something. Let's take a look at this problem. You got SO3 is being formed. You got 0.5 molar SO2. Now you have 1.0 molar NO2, not 0.5. This is not a perfect square anymore. And then you still have SO3 and NO0, okay, because the reaction is progressing to the right. So you don't have any products forming initially. During the course of the reaction, you're going to have minus X for SO2 minus X for NO2 plus X for SO3 plus X for NO. So these are the mathematical relationship. How did we get this? We're just adding that. We're going down this column. 0.5 minus X, because that's how much is being consumed as the reaction reaches equilibrium. 0.5 minus X equals the equilibrium concentration. So we leave it as a mathematical expression. Here, 0 plus X. Why? Because that's the amount of NO that forms. At equilibrium, X is the concentration of NO, as well as SO3. So we plug this into the mass action expression. Again, I told you there's a lot of math here. We get this. We get this right here. Not a perfect square. That's just x squared divided by 0.50 minus x, 1.0 minus x. And if it's not a perfect square, then you actually have to solve this brute force method. What is brute force method? You have to multiply this out. 0.50 minus x, 1.00 minus x, that's x squared, that's 0.50 x, that's 1.0 x, that's a negative and negative, and that's 0.5. So multiplying this out, this is x squared, this is negative 1.5 x, and this is 0.5. Okay, so that's the solution when you multiply that out. Now you can plug it in for the bottom here, and then you're not done. It's a quadratic equation. You've got x squared and you've got x and you got a constant, some number. You got to apply the quadratic formula. Okay, so let me just show you how that's done. This one's a little bit, again, more challenging, but it's math. It's math. The quadratic formula is something you guys should have learned in middle school or at least early high school. And you guys should know how to solve this. Or you can cheat and just get a quadratic solver in the internet. Let me show you how that's done. So let me go ahead and work this out. This is the multiplying this out, you get this value. And then you need, when you do the quadratic formula, you need to put in the form ax squared plus bx plus c equals 0. You got to put all the numbers in one side and have it equal to 0. That way you get a, b, and c, because that's what you're plugging into the quadratic formula. This is the quadratic formula right here. Okay, this would be A, this would be B, and this would be C. If I divide through by 5.85, okay, if I divide this whole equation by 5.85, then A is 1, B is negative 1.757, and C is 0.586. Now, let me just see if I have that in my computer. Let me switch gears here and let me show you, at least for these problems, what you can do is you can hedge a little bit. Okay, what do I mean by hedge? I mean that you guys can actually go into the internet and find a something called a quadratic formula solver. So let me share that with you right here. So this is, I mean, you just have to look at quadratic formula calculator. That's the keyword. So let me go ahead and plug in values for A, B, and C based on what we did. We said that A was 1, B was negative 1.757, and C was 0.586. Now, this is not cheating, unless, of course, you were taking the ACS exam and you weren't allowed calculator. This is just doing the math. This is just doing the math. And as long as you understand the chemistry, you are going to get to the correct math equation. And this is just doing the math. So when we do this, right here, it gives you the roots. Remember, quadratic formula always gives you two answers, two roots. One is 1.3. One's 1.3, and the other one's 0.447. One of these does not make sense. Does not make sense physically. You throw it out. The other one will. Now, this was when I reduced everything so that A was 1. Let me just show you that if I had did the original problem where A was 5.85 and B was negative 10.28 and C was 3.43, I should still get, there it is, it comes out to the same solution. Okay, so don't get gray hair like me doing these problems using the quadratic formula. Just find a simple app and plug it in. Okay, now that I have the solutions, that's exactly what I have right here. Okay, whether I use these or these gave me the same. Some quadratic solver asks you to put it in this form where your A term has to be 1, but most will not. Or you can do it the brute force method, like me right here. Okay, and when you solve for X, those are the numbers. It confirms what we had. Now let's see which one does not make sense. If you use this and you plug it in here, 1 minus 1.3 will give you a negative concentration. That does not make sense. So that solution is out. That solution is out. Negative concentration never exists. So the correct solution, of course, is 0.447. Okay, that's a quadratic. Now, in the next 15 minutes, I'm sorry, I'm taking a little bit longer here. It's because we're a little bit behind. I want to show you another trick. And this is the trick that you will most likely use because it's the simplest way to solve these things. But you have to recognize when to use this trick. And the trick is simplifying assumptions. Simplifying assumptions. What exactly is simplifying assumptions? simplifying assumptions is essentially that. You make an assumption that simplifies the math, okay? And more times than not in science, that's how we solve a lot of our really difficult problems, is we make an assumption. And you guys have seen this in calculus, if you've taken that, or even your complex algebra, where you make an assumption, you get a solution, you use that solution as your initial starting point, where you do a second iteration. Second iteration will give you answers that are better numbers. So that's exactly what you will see in this problem right here. So let's take a look at this problem. This is called the approximation method, method of approximation, and it's based on simplifying assumptions. So whenever I say use the simplifying assumption method, this is what I mean. Okay, this is what I mean. Now, how do you know whether or not to use this method versus a quadratic? By the way, if you use a quadratic, you will always get the right answer, the true answer, except you need to get there through a brute force method way if you need to use a quadratic solver. Simplifying assumptions get you there, usually within one iteration. It makes the math easier, okay? So let's take a look at this problem. NOCl decomposes to form NO and Cl2. So oops, I didn't want to do that. Let's just write it out. NOCl decomposes to form NO plus Cl2. This is not a balance equation, because you can see there's 2 chlorines here, 1 chlorine here. We need a 2 there and a 2 there. Okay, so that's a balance equation. And let's say that we have moles. Oops, sorry. We have moles and volume. So let's say that this is a gas, or doesn't matter what we have here. All we know is that it's a gas, or it could be a concentration. But as long as it's a gas or a molarity, it goes into the mass action expression. If it's a solid and a liquid, you still put it in the balance equation, but it doesn't go into the mass action expression. Let's do our ice table. The initial, the change, the equilibrium. It tells you right here that we're at 35 degrees. K equilibrium is 1.6 times 10 to the minus 5. And then it tells you that 1 mole of NOCl, so this is 1.0 moles in a 2-liter container. So that's 0.5. I'm going to change this. 1/2 is 0.5 molar. So that's 0.5 molar. That's what I'm going to put right here. And that comes from 1.0/2 liters. That's 0.5 molar. And then it tells you, that's the only thing that it gives you, and they give you the equilibrium constant. So we assume this is 0. And then we know that this is minus 2x. Why 2x? Because it's a 2 right here. There's a 2 right here. So that's minus 2x. This is plus 2x. Why plus 2x? Because there's a 2 right there. That's why you need to balance the equation. And this is plus x. So at equilibrium, this is 0.50 minus 2x. This is 2x. This is x. So our mass action expression looks like this. 1.6 times 10 to the minus 5 equals 2x squared. Don't forget that. Okay, why is it squared? Because there's a 2 here. So you have to put 2 twice. You have to put 2 because you're forming 2x right here, but you also need to put 2 right there because that's the coefficient in the balance equation. If you forget one of these 2's, your math is going to be wrong. So please remember that. And then this, of course, is just x. And then the bottom is 0.50 minus 2x squared. Now that looks like a difficult problem. You've got a quadratic here, you've got 2x squared here, so that's 4x squared times x, that's an x cubed. That's 4x cubed. Remember, when you square this, you square that, and then that's a square. So 4x cubed over 0.50 minus 2x squared, and that's equal to 1.6. That's when you don't have a quadratic anymore, that's beyond our class, okay? So what can you do? What can you do is go to the method go to simplifying assumptions. Go to simplifying assumption. This is not a quadratic equation anymore. Quadratic is powers of 2. This is a polynomial. There are solutions for polynomial, but we're not even going to touch that. What we need to do is go back to the chemistry. Go back to the chemistry. It's always about the chemistry. It's what I tell you guys. I tell each and every 201 student in this class. If you understand the chemistry, there is a solution. So how do we understand the chemistry? Look at K equilibrium. Remember K equilibrium I told you is an indicator of efficiency? That number is 10 to the minus 5. 10 to the minus 5. Physically, what does that number mean? It means not very much of the reactant actually converted to product. It means that this is a very inefficient reaction. At equilibrium, you still have mostly reactant. 10 to the minus 5 tells you that not much product forms. The numerator over the denominator is huge. That's why you get an exponent of 10 to the minus 5. So that's the math. What does it mean physically? Physically, it means not much of the NOCl has converted over to product. Yes, for this reaction to occur, you must form NO or Cl2. You must. Otherwise, you don't even need to solve this problem. But not much NOCl has changed. So this is the key. We can say that 0.50 minus 2x, okay? We can say that this value right here is negligible. Not much of the reactant is consumed. How can we say that? Because K equilibrium allows us to make that assumption. That's why it's called simplifying assumption. You need to make that assumption to simplify this math. If we assume that this 2x is approximately equal to 0 because of K equilibrium, then we can change this as 4x cubed over 0.50 squared. That's a problem we can solve. That's a problem we can solve because now if this is approximately equal to 0, then we can throw that out. We can throw that out. This is a problem that's doable. 1.6 times 10 to the minus 5 times 0.50 squared, you still need that squared, equals 4x cubed. We divide both sides by 4, and then we take the cube root. That's our x value. I was able to do that in like 5 seconds versus this beast right here, which would take me like 5 hours, okay? So let me show you that solution real quick. This is, see, by doing simplifying assumption, you basically take a problem that may take you a long time, a polynomial, and do it in like a minute. Let me clear this up so that you guys can see the solution, okay? Here's the solution. What we get here is we assume this right here to be 0.5 squared. And when we do that, here's the assumption. Why? Because of that. When we do that, we can solve for x. X is 1.1 times 10 to the minus 2. Now, what you need to do is compare you need to validate your assumption. 0.50 minus 0.01, that's what this number is. 1 times 10 to the minus 2 is 0.01. What is that number? That number is 0.49. It's still approximately 0.5. Okay, it's still approximately. So that simplifying assumption method works. Okay, that simplifying assumption works. Actually, this is, remember, this is 2x. So this is 0.02. 0.5 minus this is 2x. That's 0.48. 0.50 is approximately equal to 0.48. I can live with that assumption because it gives me an answer. Okay, I can live with that. So what are the equilibrium conditions or the equilibrium concentration? This chlorine is going to be 0.010 molar. This NO is going to be 0.020 molar. And this right here, if we substitute for the X value we have, is 0.48 molar. That would be the answer you would write down. Okay. Now, this simplifying assumption works because this right here is basically a true statement. 0.5 minus 2x is still approximately 0.5 to one significant figure. Okay. But in order for the simplifying assumption to work, the change over the initial, the change in that previous problem was 0.022 over the initial, which was 0.5 times 100. That has to be 5% or less. That condition has to hold. It's got to be, it's called the 5% rule. It's called the 5% rule. If the 5% rule applies, then that will work. What happens if it's greater than 5%? Then what you do is you still use the simplifying assumption, except now you use the answer in your first iteration to make a better guess. Let me show you. Okay, let's go back to this previous problem. Let me clear this out so that I can show you how to do a second iteration. And in this class, we can just go with that. 2 iterations, so we have. See how we calculated x here as 0.01. And remember, our assumption was right here. Well, what if we have a better value for x? X is not 0, x is 0.01. So 0.5 minus 0.02, because that's 2x, that's 0.48. Now, if we use this value in here, then our second iteration will be much more clean. And so that's just, let me just make sure I have this correct. That would just be 4x cubed over 0.48 squared equals 1.6 times 10 to the minus 5. You would basically just have to solve this problem. Okay. You don't have to do it in this particular case because it obeyed the 5% rule in the first iteration. But if it was greater than 5%, if that difference, the delta is this divided by the initial is greater than 5%, then use the answer from the first iteration to get a better number in the second iteration. So this right here would just be 4x cubed equals 1.6 times 10 to the minus 5 times 0.48. So I'm going to take 0.48 squared. I'm going to do that. That's 0.2304. And I'm going to multiply it by 1.6 to the 5 negative. So that's just 3.686 times 10 to the minus 6. I'm going to divide both sides by 4. And then I'm going to take a cube root on that. Okay, I'm going to take a cube root on that. And I get, in this particular case, x equals 0.09. Oops. You should double check my work. Okay. Just so that I do my math. It's 9.73 times 10 to the minus 3, or 0.00973. 0.00973 is approximately equal to 0.01. But that's a better number. That's a more true number. That's how you do the second iteration. Use the solution from the first and make your assumption better. Make your assumption better. Okay. Now, how can you tell before you even start a problem whether or not the simplifying assumption is a valid assumption to go? And this is in a different textbook. Not in this textbook, but of course I've used many textbooks over the course of my career. What you need to do is you need to do this right here. You need to take the initial reactant, divide by K equilibrium, and if it's greater than 400, then your your simplifying assumption will be less than 5%. If it's less than 400, then it's going to be bigger than 5%. Here you would need 2 iterations. Here, all you need is 1 iteration. Okay, but this is a quick and dirty way to figure out whether or not your first assumption, your first iteration will work. Here's another problem. I'm not going to work this out because we're running out of time, but here's quadratic or iteration. This is KC 7.3 times 10 to the minus 18, okay? And this problem is this. This is the decomposition of water at very high temperatures, okay? That's another way of generating hydrogen gas. And right away, you see that KC, 10 to the minus 18. You don't even need to look at initial divided by K equilibrium is greater or less than 400. That's a very small number. Iteration will work on this problem, okay? Iteration will work on this problem, no doubt. What is the iteration? You're going to assume that 0.100 minus 2x is approximately equal to 0.100. You're going to assume that much of the reactant converts over to product. Okay, and so when you do that, you get an x value of somewhere in the, look at the percent. It really does apply in terms of the 5% rule. That 0.0052% is way smaller than 5%. So this number works. You should take a look at that. Okay, here are other problems. This is a problem where we use quadratic. Okay, this is a problem where we use a quadratic. How do I know I need to use quadratic? Look at KC. That's not a small number. That's 1.8. When you have a number that's like bigger than 10 to the minus 3, okay, 10 to the minus 2, 10 to the second, you can't make those simplifying assumptions because it means that a significant amount of the reactant does convert to products. In this particular case, there's going to be a bunch of products that forms. This is the setup real quick. You do your ice table, you do your initial conditions, you do your changes based on the balance equation, and then you get your equilibrium conditions. Then you stick it into your mass action expression. And because we're not doing simplifying assumptions, you're going to need quadratic. You need to, actually, this is not too difficult because you have a square here and you have this. Well, it's still quadratic because you have an x squared. Okay, but it's not that difficult in terms of getting it to this form. And then just use a quadratic calculator to solve the problem. Okay, so right now I'm just going through this because the math is going to be either simplifying assumption or quadratic. I want you to recognize which strategy to use based on the conditions of the problem. This right here is a quadratic, okay? So this would be, let's see. Oh, this, if you take a look at this problem right here, the PCl3 and the Cl2 ends up at 0.0198. And you start out with 0.02. So this problem actually showed you that most of the reactant went to product, even though it had an equilibrium constant of 1.8. Most of the reactant actually went to product. Okay. If this was 100%, it would not be an equilibrium. The mole ratio would fit. 0.02 would convert over to 0.02 and 0.02. Okay, if it was a 100% conversion. Well, in this equilibrium problem, it converted over to 0.0198. That's very close to 0.02. So I think I left off last time with a problem in which you had to figure out whether or not is this problem actually, is it a quadratic or is it the simplifying assumption strategy? Those are the two strategies that you guys are going to use. Actually, there's three. I'll show you the third one. The first one is that the equilibrium constant and the initial concentrations do not allow for simplifying assumptions. Okay, there's a condition that I showed you last time. The second one is that the equilibrium constant is so small and the initial concentration so high. That's the two things that you have to take a look at. Then you can apply simplifying assumptions. Okay, and then the third one is, well, I'll show you in this example. Okay, so this a problem that I went over, and always pay attention to the equilibrium constant. In this particular case, the equilibrium constant is 1.8. 1.8 is not a small number, which means that most likely quadratic. Okay, and you can see right here that I've set up the ice table, the initial, the change, and the equilibrium condition. That's what the ice table is about. And it's a way to account for how the chemical changes over time so that you can get a handle on the equilibrium concentrations. Why? Because the equilibrium concentrations are what you put into the mass action expression to basically get the answers to the question. So in this particular case, I tell you that there's 0.1 moles of PCl5 in 5 liter volume. So you just do 0.1 over 5, that's the molarity. Always use molarity on the ice table or atmosphere, partial pressure. So that's what we have right here. When the chemical is not mentioned, okay, then you can assume it's 0, usually the reactant, because that's the product that hasn't been produced yet in the initial condition. Sometimes, however, you have an initial condition in which you charge the reaction vessel with product. And so we're going to take a look at that in 15.04, okay, the last section of equilibrium. Anyway, you set it up so that as the reaction progresses, it's minus x plus x plus x, and then you just write the equation based on the initial and the change equals the equilibrium. The initial and the change equals the equilibrium. And yeah, it's a math equation, but that's all you have at this point, okay? If they give you the concentrations at equilibrium, then go ahead and put that down. So in this particular case, it's just solving the math. You're setting up the products over the reactant. Remember that you have to balance the equation, because if this were 2, for example, then this is a 2x, and then of course this would be a 2x squared. But it's not, but you have to pay attention to details like that, because that's where you're going to make mistakes that is going to bite you in the end, because you know better, okay? You know better. Anyway, we solve this problem. We get to the quadratic. We set it up to ax squared plus bx plus c equals 0. We solve for the roots, and we get, there's always going to be in a quadratic 2 roots. One of them will not make sense. When you plug it into the equilibrium condition, the other one will. You throw out the one that doesn't make sense, okay? And then, of course, we have this particular solution. So we talked about this last time, and make sure you review this so that you understand the approach. It's the fundamental approach that you guys are going to be using in all equilibrium problems, okay? So let's take a look at this particular problem. 4 moles of SO3 is sealed in a 5 liter container, 1500 degrees. Kc is 9.34 times 10 to the third for the reaction whether the concentration of all species at equilibrium. This is an interesting problem in that your equilibrium constant is large. What does that mean physically? It means that the reaction pretty much goes to completion, but not quite, because there's still an equilibrium constant. As big as the equilibrium constant is large, the fact that it's an equilibrium means that you still have a reactant. It is not 0. So please keep that in mind. That's usually a true-false question I have. If the equilibrium constant is 1 times 10 to the 99, basically there is no reactant. False. you're still in equilibrium. Very, very small reactant, but you still have reactant. Okay, so keep that in mind. Let's set up this problem, and I'll show you the approach that you would take when the equilibrium constant is large. Okay, first we need a balance equation. The balance equation is SO3 decomposing to SO2 plus oxygen. Now, how would you know that? You know that because you've been exposed to enough chemistry to know that reaction, or I will give it to you. Okay, this is not a balance equation. In order to balance this equation, look at the number of oxygens there. We need to put a 2 here. We need to put a 2 there. And now that's balanced. You got 2 sulfurs on both sides, 6 oxygen in both sides. We're going to set up the ice table. Initial, change, and equilibrium. Let me change my pen here so that it's darker. Okay, and it tells you that you have 4 moles in 5 liters. That's 0.8 molar. So that's 0.80 molar. Don't put 2 times 0.8. That's what you're given. Just because you have a 2 right here, that doesn't make 0.8 1.6. Okay, the condition is that you've got 4 moles in 5 liters. The chemistry is that you need 2 SO3 to form 2 SO2 and 1 oxygen. That's the chemistry. These, of course, are gas. So they all show up in the mass action expression. This is 0 and this is 0. The reaction hasn't started yet. Then, during the progression of the reaction, this is minus 2x. Why minus 2x? You got a 2 right there. This is plus 2x. Again, you have a 2 right there, and this is just x. That part is easy. It is based on the balance equation. And then we have our equilibrium condition. This is just 0.80 minus 2x. We don't have a number here because they don't give us that information in the problem. If they gave us that information, the equilibrium concentration of SO3, then you just put it there. Then you can solve for x. But you don't have that, okay? This is just 2x. 0 plus 2x is just 2x. Remember that reactants are decreasing. That's why we have a minus. Products are increasing. That's why we have a plus. So this problem right here, the mass action expression is 9.34 times 10 to the third is equal to 2x. Don't forget this. I know you guys will. Squared. Okay, 2x squared times x all over 0.80 minus 2x squared. Why the squared? Because you have a 2 here and you have a 2 here and you got 1 there. Okay, I know it's easy to forget, and that's where you make mistakes, and then you get the wrong solution. Now let's take a look at this problem. Take a step back and always think about the equilibrium constant and its physical meaning. In this particular case, you have 9.34 times 10 to the third. That's a big number. It basically means that your reactant converts over to product, okay? It's almost like what you guys learned in Chemistry 200. The limiting reagent is going to dictate how much product is produced. In this particular case, the limiting reagent is SO3.8. But we cannot say that, okay, this, of course, will be, let me change my pen. This will be 0.8. This will be 0.4. Notice the stoichiometric ratio. And this will be 0. You can't do that because if we plug in these numbers into this mass action expression, the equation gives you infinity. Something over 0 is infinity. Something over something is equal to 9.34 times 10 to the third. It's not infinity. So you have to take a step back and think again. Okay, I know it's mostly products, so I can pretty much make that assumption. Most of my reactant goes to products, but my reactant isn't 0. So what can I do? I can say that X is approximately 0.4. Okay, I can say that X is approximately 0.4, but 0.80 minus 2x is not 0. Okay, so the x that I'm going to solve in this problem is in the denominator. So this problem translates to 2 times 0.8 squared times 0.4, because remember, x is 0.4. And so 2 times, oops, sorry, there's a redundancy there. Let me clear this. 2x is already 0.8, so I don't need that. Okay, I don't need that. I'm basically trying to do it twice. So it's 0.8 squared times 0.4 all over 0.80 minus 2x squared equals 9.34 times 10 to the third. This is a number I can calculate in my calculator. Okay, so what I will do is I will just take 0.8 squared and multiply it by 0.4. And that comes out to 0.256. That's that number. Then what I need to do is I need to do a little bit of math. This is where my variable happens to be. So I'm going to put that 0.80 minus 2x squared is equal to 0.256 all over 9.34 times 10 to the third. What I did was I just put this in the denominator and put this in the numerator. Okay, that's just the algebra that I got. And this ratio right here, 0.256 divided by 9.34 to the third, that number is going to be let me do this again, 0.256 divided by 9.34 to the third, okay? That number is 2.74, 1 times 10 to the minus 5. But it looks like you still have a quadratic. You still have an x squared here. You just take the square root of both sides. That gets rid of that square, okay? And so the square root of 2.741 times 10 to the minus 5, that's just 0.005235 or 5.23 times 10 to the minus third. I need to clear some space here, so bear with me. Okay, so what we have essentially is 5.235 times 10 to the minus 3 is equal to 0.80 minus 2x. You guys can solve that for x. Okay, that's just simple algebra. Okay, when you solve that for x, you get x as approximately about 0.39 something. I'll show you that shortly. But the rest of this is pretty straightforward. I'm not going to do the math because you guys can do that. Let me go ahead and clear this and show you what goes on next. Okay, here it is again. Again, a step-by-step showing of what's going on. Here's the assumption that you guys are going to be doing. 0.80 minus 2x is not 0 because otherwise the denominator would be 0 and then you don't have a problem to solve. But you can basically change the numerator to 0.4, at least the x value. And when you do that, you get this right here. This is where we left off last time, right here. And it equals to that. Now you can do these math different ways depending on your operation sequence. But in the end, you still get the same thing. I got x as 0.3974, which is approximately equal to 0.4, but not 0.4. Not 0.4. Why? Because if it was 0.4, this term goes to 0. It's 0.3974. Okay, so what you can do is you can take that difference, 0.8 minus 0.3974, that difference, which is the delta. That's the change in the concentration. And then divided by 0.8, and you can see that that is substantially less than 5%. So this particular problem is use via a different strategy. You don't do the quadratic, you don't do the simplifying assumption, but you assume that most of the reactant converts over to product, and then you use the concentration of the product to figure out the X value in the reactant. It's actually very close to the experiment that you guys are doing this week, okay? You're basically going to assume that the product is formed and you have to go back and calculate the reactant that you have. So that's what you would do in this particular situation. Recognize the problem based on the equilibrium constant. Equilibrium constant is really important in terms of the strategy that you choose. So that's the answer. And what I would like you guys to do, this is the problem I have in the announcement page that I posted last time. This is not due until Friday. What we'll do is break out for 5 minutes so that you guys can break up into groups. The only thing I want you guys to do is make contact with your group, get information so that you can work together on this particular problem, okay? If you are working solo, then just tell your group that you're working solo. That's perfectly fine. Let me set up this problem for you real quick so that you know what to do. What is happening here is you have it's the reverse of the previous problem. It's the reverse of the previous problem. You notice the temperature is different. That means the equilibrium constant is going to be different. Whenever you change the temperature, equilibrium constant will be different. What we have is SO2 plus oxygen gives us SO3. Okay, the Kp value is going to be 1.7 times 10 to the 8 at 600. Okay, 1.7 times 10 to the 8 at 600 Kelvin. So at equilibrium, these are the equilibrium conditions now. You've got the partial pressure of SO3 and the partial pressure of oxygen at 100. Okay, calculate the partial pressure of SO2. So that's pretty straightforward. You're already at equilibrium. You know the equilibrium conditions. You know the equilibrium constant. You should be able to solve for the partial pressure of SO2. Now, what's happening in the next part is that you still have that condition from the first, where you have these concentrations or these partial pressure of SO2, oxygen, and SO3. You haven't released anything. You haven't changed anything. The only thing that you're doing is you are adding more SO2, 0.004 moles of SO2 and 0.0028 of oxygen to the 1 liter container. So you're spiking the concentrations based on the previous problem. It's a continuation. Okay, it's a continuation. So you are spiking the problem. Then after spiking it, you're going from 600 to 1,000. Okay, after spiking it, you're going from 600 to 1,000. The reaction reaches equilibrium at 1,000, and 0.002 moles of SO3 is present. So again, that's the equilibrium condition. What would the engineer calculate for Kc and the partial pressure of SO2 for the reaction, for the conditions now at 1,000? Okay, and would you say that this reaction is exothermic or endothermic? And the way to determine that is determine whether the equilibrium constant went up or down when you change the temperature. So that's the clue I'm providing for you. Okay, this is one continuous problem. You use the conditions and the concentrations from the first problem to solve the second problem. The next slide in this particular section is just a summary. Kind of tells you, reminds you of what you need to do in order to solve these problems. Practice so that you're comfortable with these things, because this approach is just the fundamentals. You're going to do this in acid-base chemistry as well, and you're also going to do this in heterogeneous equilibrium. Okay.